Today's notes are on nuclear symbols and types of decay and reactions in nuclear chemistry. The first couple of slides are all things that are review, so I'm just going to pause on them. Please stop the recording and write down the information that you feel you need, things that you might want to recall again later, but this is all stuff that we've seen before in previous notes. So this is just a review of atomic structure. Again, take the time to pause on your own. You can pause the recording at any time on any of the different slides. This slide here is a good review of how we write a symbol for an element and a new term, which is called a nuclide. You're going to hear this quite a bit in this section. So nuclides are atoms that with the nucleus that has a given number of protons and neutrons. So in other words, any element in any form, any particular isotope of that element is a nuclide. So it's just a specialized term. Again, the element symbol is represented by X. Mass number is always given on the top. Number of protons is on the bottom. Remember, we do it that way so it's easy to subtract and get the number of neutrons. Now, we've never seen this before, but sometimes in the nuclear unit, the number of neutrons will be shown on this side. And again, you're already familiar that the charge is over in the upper right-hand corner. And again, that the protons and the neutrons are added together to equal the mass. Now, a few other terms that you should be familiar with. Again, we talked a little bit already about isotopes and early in the year and last year. Again, an isotope are elements or atoms of the same element that have a different number of neutrons. Therefore, they have different masses. Okay? Things that we've gone over before. So again, just replacing that term, a nuclide with the same number of protons but different number of neutrons. Isotones are nuclides with the same number of neutrons but a different number of protons. And then isobars are nuclides with the same mass but different numbers of protons. So atoms that have the same mass but have a different number of protons and neutrons and therefore are different elements. Now, the majority of our notes today are on different types of nuclear transformations. And there are two types, decay and reaction. I highly encourage you to make sure you have the examples written down as we go through, especially the next 4 slides. So, nuclear transformations, decay. If you think about that term, we've talked about that before, and especially in biology, we use this term quite a bit. Decay means to break down. So we take something larger and we break it up into smaller parts. The key thing with nuclear reactions, whenever you are writing any of them, is just like balancing a regular equation, except for now we're balancing the number of protons and neutrons. So in a decay reaction, we have a big thing breaking up into 2 smaller items. And there are different types of decay. This is just a sample one. We're going to take a look at the different types of decay reactions here in a moment. So we have to make sure that the numbers on the left equal the numbers on the right. So 238 for our mass is equal to 234 and 4, which gives us again 238, 92. 90 plus 2 is 92. So make sure that, again, you're following the law of conservation of matter, that matter cannot be created nor destroyed. So that's protons, neutrons, and electrons also. So everything has to be balanced. Now, a reaction in this unit is going to be when something is added onto the left side. So an atom takes in something else and then is modified and becomes something, another version of that atom or another atom entirely. Now, our different types of decay reactions that we are going to take a look at. The first is the alpha decay. Alpha decay occurs when an atom ejects an alpha particle from its nucleus. Okay, an alpha particle is basically just a helium nucleus. The electrons are missing, it's a helium nucleus. So therefore it has a +2 charge. These are huge particles. Again, you remember Rutherford's experiment, he shot alpha particles, so these positively charged particles that come from this new type of nuclear decay. They're so big, they're stopped by a piece of paper. Here's an example. Again, this is the one from our notes. So you aren't going to have to come up with what type of decay most of the time in a problem. You're going to be told. So you need to know alpha decay is the production of a helium nucleus. So again, helium has a mass of 4 and it has 2 protons. So that's where our numbers are coming from. And so we have to make sure that, again, that adds up with our other element. So trying to figure out what goes here is basically what your task will be. So you know what you're starting with, you know the type of decay, you should be able to subtract and figure out what your new element is. So 238 minus 4 is 234, 92 minus 2, because it's alpha decay, gives us 90. You look that up on your periodic table, and that's thorium. Another type of decay is called beta decay. Beta decay occurs when the nucleus ejects a high-speed electron. Remember, electrons are negatively charged. Essentially, they have no mass, so that's why we've got a 0 up here. And they are stopped by a thin sheet of foil. Okay, so let's think about what happens here. So beta decay, a high speed of electron comes flying out of the nucleus. Okay, so if we started with carbon 14, our mass is still going to stay the same because electrons don't have any mass. But because of that negative charge, in order to have our sides be equal, we have ended up with nitrogen. So essentially, as we are looking at this, thinking about this, when we lose a negative out of our nucleus, we've gained a proton. So beta decay essentially causes the gain of a proton in the nucleus of the atom. And so now we have nitrogen in this example. A third type of decay is called positron decay. All right, in positron decay, we have a high-speed, positively charged electron, hence the word positron, that is ejected from the nucleus. Positive charge because it's positron, same mass as an electron, which again gives us 0 out here, stopped also by a thin sheet of foil. So this time, as we are looking at it, we have a positive charge that is being ejected from the nucleus. So that is overall going to reduce our number of protons. If we lose a positive from the nucleus, we have reduced our number of neutrons. So our mass is still the same, 30, but because of that positive charge that's coming out of the nucleus, we now are down to only 14. So phosphorus and now becomes silicon with that conversion and loss of that positron. Now, this is an example of a nuclear reaction. We have electron capture. Okay, think about what the word capture means. To me, I think capture means to grab onto, to take in. So electron capture is when the nucleus of an atom captures an electron, steals it out of the electron cloud. And you can see that here in the picture where the electron is coming out of the electron cloud and becoming part of the nucleus. Effectively, when we add an electron to the nucleus, think about it, I put a negative in here. A negative is going to counteract that proton. So it's going to convert that proton to a neutron. And it is not detectable with a Geiger-Müller counter, and that's what's used to be able to detect radioactivity. So again, all these things are different forms of radioactivity and radioactive reactions. So in our example here, again, electron capture. This is the type where the substance is taken in. So we have our negatively charged electron being added onto this atom. Our mass, again, does not change because electrons don't have a mass, but a negative is going to cancel out one of those protons from chromium, and we now will end up with vanadium as our element. Couple other things that we should review as we are working our way through this unit is the electromagnetic spectrum. So take a moment to review through that, what we have talked about before. And we have a few formulas down in the bottom again that we used last year and when we were doing review, that the speed of light is equal to the wavelength times the frequency, and energy is equal to h. Planck's constant, which is this number down here, 6.6, I always use 626 times 10 to the negative 34 joules times seconds times the frequency. And again, c, of course, the speed of light is 3.00 times 10 to the 8th meters per second. Our last type of decay is one that we aren't going to really have any examples in the homework, but this particular one is one that you should be aware of because we have talked about it and heard about this before, and that is gamma decay. And gamma decay is just a form of electromagnetic wave, and we took a look at the electromagnetic spectrum on that last slide. They have no charge, there's no change to an atom's identity, no mass, and it is powerful enough that it goes through several centimeters of lead. All right, and again, we think about examples of where we talk about gamma decay besides certain elements that undergo gamma decay. All right, mostly we are thinking about this gamma rays and stuff coming from outer space is where we have discussed that before. Now, the rest of your time today, you are going to go through the basic types of radioactive decay, the alpha, the beta, and the positron, and then, of course, electron capture, and review those with a little bit of homework. So your homework assignment is in the textbook, and I've also posted that to Edmodo for you. So good luck with those. Again, the answer keys on the front desk, and feel free to check your way through those. So have a great weekend, and I will see you on Monday.